So I want to thank first the organizer for giving me this opportunity, and I'll talk about our recent work on topological semi-metal. Here is the outline. I'll review briefly the topology in condensed matter physics in the context of this topic, and then topological semi-metal, and that will be followed by nodal line semi-metal, which is the topic of this talk, and it's protected flat surface states. Yeah, so topology occurs both in interacting and non-interacting, interacting and interacting and non-interacting fermionic systems. There are many fermionic non-interacting topological systems. For example, integer quantum Hall, charge insulator, quantum spin Hall insulator, wild semi-metal nodal line, and so on. The different name suggests that there are different kind of topological invariant exist in these systems, and that comes from the different symmetry the system has. And these systems are simpler to understand than its interacting counterpart, like fractional quantum Hall insulator, fractional charge insulator, and so on. My topic belongs to the first category. Yeah, so in band theory, topology is defined only for gapped band structure. A topologically non-trivial phase is distinguished from a trivial phase or from another topological phase by a topological invariant, which I denote as C. And it has the property that it cannot change under any small deformations or perturbation of the Hamiltonian. And this quantity is defined, is given by an integration of some object over the Brillouin zone. Yeah. So this quantity, this F here, is constructed from the wave functions of the block wave functions. From the block wave function U and K. It can be, depending on the symmetry, it can be many things. For example, in time reversal broken system, if it is a charge insulator, then this would be the Berry curvatures. And note that though the right-hand side quantity depends on the parameter M of the Hamiltonian, the left-hand side quantity C is independent of that. That's the topological information. It's a reflection of the statement here. Yeah, so now given to band insulator, how can we say whether they are topologically identical or they are different? So if I find some perturbations or let's say some path, or I can tune some parameter in the Hamiltonian to go from one insulator to the other without closing any bulk gap, then I say that they are topologically equivalent or identical. If this two insulator has, let's say, two different invariants C1 and C2, this is my parameter space, 2V. Then if I go from this topological insulator to this one here with different invariant, then necessarily there will be a bulk gap closing. And this leads to, this is non-adiabatic path, and this leads to the existence of a special kind of surface state which lives in the bulk gap between conduction band and valence band. And these are the hallmarks of many topological systems, the existence of surface state, which are the metallic, though the system is insulator. Yeah, so the topology occurs not only in insulator, but also in metal and semi-metal. This has been understood, or people have understood in the last decades. So topological semi-metal are systems where valence and conduction band have a robust touching point in the K space on the Brillouin zone. For example, in Dirac, I have changed something, yeah. For example, in Dirac semi-metal, two degenerate bands. So degenerate bands, this conduction band and valence band, touch at a point, and the dispersion around this touching point is a linear, which is given by simply a Dirac Hamiltonian, gamma dot K. Gamma is 4 by 4 gamma matrices. For wild semi-metal, the non-degenerate band touch an even number of points in the Brillouin zone, and the Hamiltonian around each of the touching point is given by basically the wild Hamiltonian K dot sigma. A nodal line semi-metal, this two band touches on a closed line in the K space. Out of these three semi-metal, wild semi-metal is the most robust topological phase. It does not require any symmetry, not internal symmetry, not crystalline symmetry. However, Dirac semi-metal requires crystalline symmetry. Internal symmetry is not enough to protect this kind of touching points. In nodal line semi-metal, like Dirac semi-metal, it is believed that so far it also requires crystalline symmetry. It requires symmetry to protect this kind of touching. And today, the general understanding is that you cannot get this kind of system with internal symmetry. So by internal symmetry, I mean time reversal, charge conjugation, or particle hole in the context of condensed matter, and chiral symmetry. So this is what I will show in this talk, that it is possible to obtain nodal line symmetal, this kind of protected touching with internal symmetry alone. So what is topology in semimetals? So this is a gapless system. So how do you define that? So the definition is kind of like insulator. So for any small deformation or perturbations, you will not be able to gap out the systems or remove these touching points. All it can do is just shift this touching point in the Brillouin zone. So there must be some topological invariant which protects this touching point. So how to see that? Let's take an example here. So this is my 3D Brillouin zone, and this red dot is some touching points of valence band and conduction band. And I enclose this touching point by lower dimensional manifold in the K space. So for example, in 3D BZ, this will be sphere. It need not be sphere, but it should enclose. By construction, the Hamiltonian restricted on this enclosing surface is insulator. So I can classify according to the periodic table of topological insulator. For example, in wild semimetal, the Hamiltonian restrict on this describes a Chern insulator. So this is a Chern number which protects the topology in wild semimetal. In nodal line semimetal, you can have multiple dimensional topological invariant. So for example, this is my black line is the touching points in the Brillouin zone. I can take 2 points inside and outside, and I can define invariant where system is gapped. So it's a 0-dimensional invariant. Here I can enclose it with a loop. This is 1-dimensional invariant, or here it's 2-dimensional surface which enclose it. So I can have multiple dimensional invariant, and that depends on what symmetry you have in the Hamiltonian. Yeah, to understand the band touching in semimetal, which involves generally 2 band, valence band and conduction band, it is a good starting point to take a generic 2-band Hamiltonian like this one. So yeah, and now we ask what is the gapless point, and for that, these 3 functions, f1k, f2k, and f3k must vanish, and you have 3 functions and 3 variables in 3D, kx, ky, kz. So this will give you some unique solutions, and that are generically Dirac points. So how to get, now if you add any perturbations, this is all the polymetries are used up here. It all can do, it can shift, but cannot remove these touching points immediately. Now the question is, how can we get nodal line touching? For that, one of the f(k) must vanish identically. Then I am left with these 2 functions, and each of the functions describes surface in 3D whose intersection is a solution, which is a nodal line. But this requires additional symmetry or fine tuning. So further, it's believed that nodal line symmetry cannot be stabilized by internal symmetry alone. So you require crystalline symmetry. But here we claim that it is possible with internal symmetry alone, and the symmetry we consider the chiral symmetry. So chiral symmetry acts on the block Hamiltonian HK as like this. So it's basically anti-commute with the Hamiltonian for wall K. And after imposing this, you get this simple Hamiltonian. And obviously the solution space is a nodal line semimetal because you have 2 functions and its intersection is a nodal line. Yeah, however, there are caveats. It looks like we solved the problem with this chiral symmetry. So this is a very simple model with 2 band, and it doesn't involve any spins. So you have full AC to spin rotation symmetry. There's no spin orbit coupling, and there are some unwanted symmetries here also. So to really show that you can have topological nodal line symmetry with internal symmetry, you have to consider a generic spin orbit coupled Hamiltonian, which involves many number of bands in general. So there's a natural way to do that because we have a chiral symmetry, which is the main thing. So we look at Fourier table of topological insulator and superconductor. So this is the Artland-Jumbo symmetry class, chiral class. So the different classes are labeled by the set of 3 symmetry: time reversal, charge conjugation, or particle hole, and the chiral. So depending on which symmetry you have or not, you have different kind of classes. Now the important thing is that in dimension 3, except BD1 class, all 4 chiral classes has topological, non-trivial topological index. So that means if you take a generic model in these classes, chiral classes, then if you tune the parameter, then the transition always involved from topological to trivial a gapless points. Now we ask the question, is it a stable gapless phase? And what is the nature of this gapless phase?
You have 2 minutes.
Yeah, so to answer that, we have to basically construct a general Hamiltonian for each of these chiral classes. And we take here one representative example, is the class C2, which is defined by this condition that time reversal operator and charge conjugation both should be squared to -1. And this gives the constraint that the Dirac Hamiltonian must be 8 by 8 component. And this is the most general Hamiltonian in this class C2, the minimal Dirac Hamiltonian. C80K is the simple Dirac Hamiltonian with only 4 gamma matrix, and additionally you have 14 terms. And it is a challenging task to get to find the gapless phase it has. However, we are able to manage it to find the gapless phase. And if, this is our solutions. We find that there are pair of nodal loops which are related by time reversal symmetry, and they carry a same topological charge, identical topological charge. And this is we have shown for all the chiral classes. For example, class A3, C1, and D3. C2 is the most involved case. And the class C1 and D3, we get this opposite topological charge. And this is our the main result, that in all the 4 chiral classes, there exists a stable gapless phase, and it's generically a topological nodal semimetal. Yeah, so, and the most interesting, one of the interesting things, and also as well as a good signature of topological nodal semimetal is the existence of flat surface states in the finite region of the Brillouin zone. And this you can understand from the fact that this is a 3D Brillouin zone. The black loop is the gap closing point, and if we take a enclosing line or loop, because this is a Brillouin zone, so this is periodic, the orange loop and the blue loop. So as long as the orange loop lies inside this black loop, I can define a Hamiltonian. It's a 1D Hamiltonian. It's by construction, it's a insulator. So it has 8 states. So for all kxqi values inside that, I will have the surface state. That's the reason for I have a flat surface state. And now this is a representative case for the surface state in class C2. In summary, we studied the nature of the gapless phases in the chiral classes, and we proved that or show that there exists a stable gapless phase in the 4 chiral class, and it has a topological protection, which is a topological nodal semimetal. It has robust flat surface states. So that's it, and I want to thank ICTS for hospitality and support, because the part of the work is done here. Thank you very much.